In this video, we come back to the question of stability for difference equations of the form xt plus 1 equals f of xt. And I would like to use cobwebbing to get an idea about stability. For that, I show you functions here which are monotonically increasing, and then on the next slide I show you functions which are decreasing. Now we learned already that the intersection of the diagonal with the function itself gives us the equilibrium points or the fixed points. So here, for example, the fixed point is right there, here the fixed point is right there. Now for these typical situations, I would like to use cobwebbing to try to understand stability of the corresponding fixed point. So for example, here on the left, so I start somewhere here, and I go up to the curve, to the diagonal, to the curve, to the diagonal, and it looks like I'm converging closer to the fixed point. If I start here, let's say at 0.7, I go to the curve, to the diagonal, to the curve, and I'm also converging towards the fixed point. So it is very clearly asymptotically stable. So let's give it a name. Let's maybe call this x hat, and then it's asymptotically stable. But now, let's understand this better by looking at the derivative of the function at the fixed point. Okay, so f prime at x hat is the slope of the tangent line at the intersection point. So here I indicate the tangent line at the intersection point as a gray line. Okay, and the slope is f prime at x hat. So the blue curve is increasing, which means the slope is certainly positive. The red line has slope equal to 1, which means the blue line has a slope less than 1. So this is the case here, and in this case we seem to find asymptotical stability. Let's look at the next case. Here I start cobwebbing. I go to the function, to the diagonal, to the function, to the diagonal, to the function, to the diagonal, to the function. So I clearly move away in this case. And guess what? If you start on top of it, I also diverge away. So here it appears that x hat is unstable. Same question about the slope. So the slope of the blue line, it seems to be steeper than the red line, so the slope is bigger than 1, and of course it's positive as well. So here we have f prime at x hat seems to be larger than 1. If f prime is less than 1, we are asymptotically stable. If f prime is larger than 1, we are unstable. So this looks like a really cool criterion where we can use the derivative of f. So let's see if this works for the negative slope functions similarly. Again, let's start cobwebbing. For the blue function, the right diagonal, the blue function, etc., etc. And you see I'm clearly converging towards the fixed point x hat. So here again x hat is asymptotically stable. But not only am I converging to it, I'm also oscillating around it. Right? I go above, below, above, below, above, below. Let's look at the derivative. F prime at x hat. First of all, we know it is less than 0, right? Because we have a decreasing function at the intersection point. But then it is a little bit harder to see than before. It is in fact not as steep as perpendicular to the red curve. So the slope is not as steep as -1. So in this case, f prime is between -1 and 0. In the next picture, f prime is still negative, but it is much steeper. In fact, it is less than -1. And see what happens here. So then I start somewhere, and I am driven away, as you might have expected already. So here I am driven away. X hat is unstable. And believe me, this is the case when f prime of x hat is less than -1. And again, we seem to have a criterion looking at the gray expressions here happening at -1. So let us summarize this in a little theorem. Suppose x bar is an equilibrium point of the difference equation xt plus 1 is f of xt. F is differentiable, f prime is a continuous function. Then, if the absolute value of f prime at the fixed point is less than 1, then we are in the asymptotically stable case. If the absolute value is bigger than 1, then we are in the unstable case. And finally, If the absolute value is equal to 1, then actually it could be either way. It could be asymptotically stable, it could be unstable, or it can even be neither of those. So let's do that for one of our favorite examples, which is the logistic map given here. Xt plus 1 is c xt times 1 minus xt. We have the equilibria 0 and 1 minus 1 over c. And so to identify stability now, we need to differentiate and then look at the derivative at 0 and the derivative at 1 minus 1 over c. The updating function f of x is cx 1 minus x. I multiply this out, this is cx minus cx square. And so then f prime would be f prime of x is c minus 2cx. So f prime at 0 is then c minus 2c times 0, which is c. Now the criterion on the previous slide says that if absolute value of f prime is less than 1, then we have stability. And if the absolute value of f prime is bigger than 1, we have instability. So what we need to look at is the absolute value of c less than 1, then we are asymptotically stable. So meaning that c is in the interval of minus 1 and 1. Then we are asymptotically stable. If c is less than minus 1 or c is bigger than 1, then we are unstable. Good, let's do that for the other case. So again we take f prime and then we sub in the value 1 minus 1 over c. So then we have c minus 2c times 1 minus 1 divided by c. Multiply this out, c minus 2c plus 2, which gives 2 minus c. And again, for stability, we are interested when is 2 minus c less than 1 in absolute value. Well, this in fact are two inequalities, so we need to satisfy minus 1 is less than 2 minus c is less than 1. And so let's call these inequalities inequality 1 and inequality 2, and let's look at them separately. So inequality 1 reads minus 1 is less than 2 minus c, and I bring the c on the other side, so this implies that c is less than 3. And let's look at inequality 2, which says 2 minus c is less than 1, so this implies that 1 is less than c. So together we get two conditions, c must be between 1 and 3. So for c between 1 and 3, the equilibrium 1 minus 1 divided by c is asymptotically stable. So here on this table I have written the cases. If c is between 0 and 1, then x hat is stable. And there's an example right here where c is 0.8. 0 should be stable, and if I do cobwebbing, it is stable. The next case, when c is between 1 and 2, then x hat is 0, becomes unstable, and 1 minus 1 over c arises and becomes stable. So this is this case. And indeed, the upper fixed point is stable, 0 is unstable. If c is between 2 and 3, then we should get oscillations. So then let's see. Here and here and here and here. And then we do oscillations around the fixed point, but it's still stable. And then if c is bigger than 3, here is c is 3.2, it should be unstable. So maybe I start close to it, and I should be driven away, which indeed is the case. And x hat is unstable and oscillatory. And then if you carry this further, here c is equal to 3.8, then you get these chaotic dynamics. Let me summarize. So we take a smooth function, which means f prime, I assume, exists, and f prime is a continuous function near x hat, and then we have a stability criterion involving the derivative, which is if f prime at x hat, which is f prime at the equilibrium point, is less than 1, then we have asymptotic stability of x hat. And if the opposite is true, if the absolute value of f prime at x hat is bigger than 1, then we have the unstable situation. And we saw two cases for increasing functions and for decreasing functions at the fixed point. If the function is decreasing at the fixed point, then this is an indication of oscillations. Furthermore, we have seen very interesting, even chaotic dynamics of these systems. Marlo? Geller? Let's see if we really got it. Yippee! Yay!